Moving on into our next concept, and that's Lewis structures. Lewis structures absolutely 100% depends on understanding electron structure that we've been working on for a while now. So we have hopefully made the connection that our shell models, let's say this is a shell model of carbon, that would be 6 protons in the middle, 2 core electrons, and 4 valence electrons. So 6 protons, 6 electrons, and that's 2 core, and 4 valence. So this we have called our shell model. This is a full shell model. But we have also drawn simplified shell models. Where we take number of protons minus number of core electrons, and that equals our core charge. So plus 4, and then we've got an empty first shell, and then our second shell will have 4 valence electrons in it for carbon. We have hopefully recognized that core charge for a neutral atom is equal to the number of valence electrons. So core charge and valence electrons are equal for a neutral atom. Okay. The periodic table tells you is very handy and can tell you how many valence electrons something has because it's all based on group number. I'm not going to draw a super awesome periodic table down here, but yeah. Ignoring these transition metals, this is group 1, group 2, group 3, 4, 5, 6, I need another 7, and then there's our group 8. This top line shouldn't exist. Yep. That's what happens when you're just drawing it on the fly. So our group number tells us our core charge and our number of valence electrons. So carbon is sitting right there. It's in group 4, so carbon has a plus 4 core charge and 4 valence electrons. What does it have to do with Lewis structures? Well, we're going to form compounds. Why do atoms come together to form compounds? We were talking about shell models and electronic structures of atoms, but atoms coming together to form compounds, they do that because they can get to a lower energy state by doing that. And when they come together and make bonds, what kind of electrons are involved in bonds? Valence, not core, only valence. And so we will represent our valence electrons with our Lewis dot structures. Lewis dot structures are basically simplified shell models. It's even simpler than the simplified shell models, but Lewis dot structures are simplified shell models. So if we're drawing a Lewis dot structure of carbon, carbon has 4 valence electrons. Put the electrons at the points on a compass because we've also said electrons don't pair unless they have to. So we put electrons at 4 points on a compass, and it doesn't matter if we do north, south, east, west. If we only have 3 electrons, north, south, east, it doesn't matter. But 4 points on a compass for 4 carbon valence electrons, 4. That's my Lewis dot structure of carbon. It's that simplified shell model. It's too many clicks backwards or I would go backwards. It's that simplified shell model with 4 valence electrons. We're just not showing the core charge. That's all it is. So if we draw a Lewis dot structure of oxygen, oxygen is in group 6. So oxygen has 6 valence electrons. So we put a little O symbol, and we put a 1, 2, a 3, a 4, and then we have to start pairing. 5, 6. It doesn't matter if you drew it this way or if you drew it symmetric because you want it to be symmetric. It doesn't matter. All of these are representative of oxygen's Lewis dot structure. There's the other option where you can have 2 in the bottom left-hand corners. Yes, lots of options. It doesn't matter. 6 valence electrons around an O. That's O's Lewis dot structure. If we draw a Lewis dot structure for chlorine, aluminum, neon, sulfur, chlorine has 7 valence electrons because it's in group 7. Aluminum has 3 valence electrons because it's in group 3. Neon has 8 valence electrons because it's in group 8. And sulfur has 6 valence electrons because it's in group, you guessed it, 6. So chlorine, 1, 2, 3, 4, 5, 6, 7. Aluminum, 1, 2, 3, done. Neon, 1, 2, 3, 4, 5, 6, 7, 8. All right. Sulfur, 1, 2, 3, 4, 5, 6. It's that easy. Draw Lewis dot structures. You may notice the periodic table gives you all the hints on how these things should be drawn. If it's in group 1, you got 1 dot. If it's in group 2, you got 2 dots that are not paired. If it's in group 3, you got 3 dots. Group 4, group 5, group 6, group 7, group 8. Uh-oh, helium's an outlier. We'll talk about that one. Hopefully you already know why that one's an outlier. So as you'll notice, I've picked the alkali and alkaline earth metals plus the P block. So really the S block and the P block. We have completely left out the D block. Those things do strange things, those transition metals do strange things sometimes in Lewis structures. So we're not really going to draw a lot of Lewis structures with those. All right. Way back when, I don't know, August, September, way back when, we talked about classifying compounds as ionic or molecular. And when we talked about classifying something as ionic and molecular, what did we use to describe ionic and molecular? How do we know if it's ionic or molecular? Ionic means metal plus nonmetal. And molecular means nonmetals only. So this compound is nonmetals only. This compound is a metal and a nonmetal. Hopefully we remember who are metals and nonmetals on the periodic table, but we can go back and revisit. If I point out a couple of things here, there is melting point of this ionic compound and a melting point of this molecule. There is a boiling point of this ionic compound and a boiling point of this molecule. And one more, there is the molar heat of vaporization, it's a delta H thing, for an ionic compound and a molecule. All 3 of those have significantly different numbers. And significantly different numbers tells me there's something different about ionic and molecular compounds. The bonding in ionic compounds is different from that of molecules. Ionic compounds, the 2 pieces, the metal and nonmetal, are selfish and not selfish. I'll explain what that means. The molecules are good at sharing. Let's explain. Ionic compounds make ionic bonds. Okay, so what? Lithium, his Lewis dot structure looks like this with 1 little dot. Fluorine looks like that with 7 little dots. Well, if fluorine could gain 1 electron, it could be like a noble gas. And if lithium could lose 1 electron, it could be like a noble gas. Not a mobile gas, a noble gas. So if lithium loses and fluorine gains, both of those end up like a noble gas. And as we've already discussed, noble gas configuration is stable. So this is like a match made in heaven where lithium can completely give up its 1 electron to fluorine so that fluorine is totally full and lithium's valence shell is totally empty. Lithium becomes a plus, fluorine becomes a minus. This lithium fluoride is a metal-nonmetal ionic compound. Metals always give up electrons because that makes them more noble gassy. And nonmetals always accept electrons because that makes them more noble gassy. Does all that old stuff start to make a little more sense now? I hope so. My 1s2, 2s1 becomes, I got fluorine next. My 1s2, 2s2, 2p5 becomes a 1s2 like helium, and a 1s2, 2s2, 2p6 like neon. This product is like two noble gases coming together. It's a weird kind of way to look at it, but there is total electron exchange in an ionic bond. That's my point. In a covalent bond, that's not so. In a covalent bond, there's sharing. Sharing is caring. These things are much better at sharing electrons. Why would they share? Because if they share, they can each have a full shell. So fluorine has 7 dots and 7 dots. But if these fluorines get close enough to each other, then instead of having 7, they can share the 2 in the middle to where this one has 8 electrons, also known as a full second shell. And this one also has 8 electrons, also known as a full second shell. If they get close enough, they share the 2 in the middle. So how do we draw Lewis structures when you share? You don't really draw them as dots share in between. Couple of clicks. Hold on, I'm going to get there. You don't really draw them as dots in between. Come on. You draw them as a line in between. A line represents 2 electrons being shared between 2 nonmetal atoms. Whew, yeah. Okay, so these things, it's called a covalent bond. So these 2 shared electrons, covalent bond. The electrons that are not involved in bonding are called lone pairs. So we would look at this F2 molecule and say there are 2, 4, 6, 8, 10, 12 lone pair electrons, CCC, and 2 bonding electrons. Every line is representative of 2 electrons. Okay. What does the energy diagram look like? We're closing out our energy chapter, getting started on our Lewis structure chapter, but we got to talk a little bit about energy anyway. When 2 F atoms are very far apart in space, that's a high energy state. But when they come closer together, it decreases in energy. This is not the ideal distance, but they're getting closer to ideal. Eventually, they do get to an ideal distance where the F atoms are just close enough to share so that each of them experiences a full second shell feeling in their a noble gas-like state in their second shell being full. Yeah. If those F atoms get even closer together than they are right here, energy skyrockets. Because those 2 F nuclei get too close together, and those 2 positively charged nuclei start to repel each other. So this kind of diagram shows us the distance, the ideal bond distance for whatever type atom. This is a fluorine molecule. Whatever type of molecule we're talking about bonding, if we put an actual value on the x-axis, that would tell us the bond distance for a F2 molecule. Okay. One little thing, because this is an energy plot, if I have an F2 molecule and I put in enough energy to rip away those atoms, that's breaking the bond, breaking the covalent bond that's sticking those 2 fluorines together. That's a bond dissociation energy. How much energy does it take to rip those 2 fluorines apart? Whew, okay. So that's F2. That was a diatomic molecule. We used it as a description for how electrons are shared within molecules. But water is also a molecule. Water is a hydrogen atom, an oxygen atom, and another hydrogen atom. If we take the Lewis structure of hydrogen and the Lewis structure of hydrogen and combine it with the Lewis structure of oxygen, we need these things to share so that they can each experience full shells. So if my hydrogen and oxygen get close enough together, this little vacancy and that little vacancy can be filled. If my hydrogen and oxygen get close enough together, this little vacancy and that little vacancy can be filled. So we would say oxygen, ... can share 2 electrons with a hydrogen. Hydrogen only wants 2 electrons in its valence shell, right? Because it only has the first shell available to it. So hydrogen has 2 electrons, Hydrogen has 2 electrons. Oxygen has 8 electrons. Something that students are frequently confused about when talking about Lewis structures. Lines count twice. So shared electrons count for both atoms. So these 2 electrons count toward hydrogens being full. These 2 electrons also count toward oxygen being full. So when I say oxygen's got 8, that's because I'm counting 2, 4, 6, 8 around oxygen, 2 around hydrogen, 2 around hydrogen. If I had drawn it this way, maybe we could see that a little better. But we really don't draw dots shared this way beyond our first day of learning Lewis structures. But we can see maybe how those 2 electrons are hydrogens and those 2 electrons are hydrogens. And these 8 electrons are oxygens. Those 2 electrons are in 2 circles. Oh, yeah. All right. We would say that water has 2 lone pairs of electrons, also known as 4 lone electrons. So the 2 lone pairs, we're counting those as pairs of electrons, or 4 unshared electrons, and 4 shared electrons. 4 shared electrons. That's 2 4. All right, I think I got water's Lewis structure. I'm ready to move on to something else. If we talk about carbon dioxide, that's carbon. It has 4 valence electrons. Oxygen, that has 6 valence electrons. And oxygen, that has 6 valence electrons. So the number of valence electrons can also tell me how many bonds a molecule likes to make. Because everything in the second period of the periodic table, so that's the second row, everything in the second row wants to be like neon. And neon has 8 electrons in its valence shell. Everybody wants to be like neon. Everybody's aiming at 8 electrons in its valence shell. So oxygen is 2 electrons away from 8. Oxygen is 2 electrons away from 8. And carbon is 4 electrons away from 8. What that tells me is oxygen likes to share 2 electrons with something else, and carbon likes to share 4 electrons with something else. What am I saying here? I'm saying it seems like this could be a good sharing pair, and this could be a good sharing pair. But I've still got these that could be a good sharing pair, and those that could be a good sharing pair. Are you following along with me, even though that's crazy loopy-loopy stuff? I'm saying carbon and oxygen can share like this and share 4 electrons between them, like this, giving me 8 electrons shared by that oxygen, not all shared, 8 electrons in that oxygen's valence shell, 8 electrons in that oxygen's valence shell, and 8 electrons in this carbon's valence shell. The way that looks with sticks is like this. Oxygen has 2, 4, 6, 8 electrons around it. Oxygen has 2, 4, 6, 8 electrons around it. And carbon has 2, 4, 6, 8 electrons around it. That's called a double bond. These are called double bonds. Yeah. There's our official definition. A double bond is 2 atoms share 2 pairs. A triple bond is when 2 atoms share 3 pairs of electrons. Come on, PowerPoint. There we go. A nitrogen, diatomic nitrogen, is one example of a triple bond needing to form. So that nitrogen has 2, 4, 6, 8 electrons on the left nitrogen, 2, 4, 6, 8 electrons on the right nitrogen. The 6 electrons in the middle are shared by both nitrogen atoms. Yep, we got it all. 4 lone pair electrons, 6 bonding electrons. That's enough of an introduction to Lewis structures, but we're going to build on our Lewis structure model swiftly, so be ready for it. Make sure you know how many valence electrons something has, because we've got to hook them up into all kinds of combinations of molecules soon. Goodbye.